Yeah. Shall we get started? Where are others? ஏன் டெய்லி லேட் ஆகுது வந்துட்டு இருக்காங்களா? சரி, நம்ம வில் ஸ்டார்ட்.
Good evening, sir.
Yeah, good evening. Right. So we'll get started. So in the last class, we started discussing about some terms that are related to magnetic substances. So what were they? One is called as the magnetizing field. Then we saw what is magnetic induction. Then we saw what is the intensity of magnetizing field. That is the magnetizing field intensity. Right? And we saw what is intensity of magnetization. Right? Yeah. See, we saw what is intensity of magnetization also. What is it? It is defined as the amount of magnetic dipole moment developed per unit volume when the substance is placed in the external magnetic field. We also saw the formula for it. For magnetization, the symbol used is capital M. This is equal to N into IM, where IM is called as the magnetization. I gave a term name for it. It's called magnetization. Look at the second point. N into IM, it's called as magnetization surface current. Right? So based on this, we saw an important relation that exists between B naught and Bm. So what did we see? B is equal to B naught plus Bm. So what is the value of B naught? B naught is mu naught into H plus Bm is equal to mu naught into capital M. So this will come out to be mu naught into H plus M. Am I right? Right. This is a relation. Right. After this, we saw what is magnetic permeability. You remember what it is? So what is magnetic permeability? It is represented by the symbol mu. So it is the, guys, settle down fast. It is the measure to the extent, sorry, it is a measure of the extent to which a material can be penetrated or permeated by a magnetic field. Means how much does the magnetic substance allow the magnetic field to penetrate through it is defined by this parameter called as magnetic permeability. And how is magnetic permeability defined as? It is defined as the ratio of B and H. It is B divided by H. Right? It is B divided by H. So what is going to be the SI unit for it? It is going to be Tesla meter per ampere. And what is going to be the dimensions for it? Dimensions of mu is ml minus 2, A minus 2. Is it clear? It is ml minus 2, A minus 2. Done? So we'll start with the next term, that is relative permeability. So the previous one that we saw was permeability. Now we are going to see relative permeability. So relative basically means it is a comparison. So it is a comparison, right? So what does it state? Permeability of various magnetic substance can compare with one another. So since we saw what is the permeability of a material, which defines the extent to which the magnetic field can penetrate through it, if you are able to compare the permeability of a substance with the permeability of known substance, that is vacuum. If you are able to define mu divided by mu naught, then this parameter is what is called as relative permeability and is represented by the symbol mu with a subscript R. Is that clear? So it is defined like this. It is defined as the ratio of permeability of the medium to the permeability of free space. Right? And when it comes to the unit of it, it does not have any unit because it is a ratio of the same physical quantity and it is a dimensionless quantity also. Is that clear? So when you talk about the relative permeability of vacuum, it is 1 because you will be mu naught here and mu naught here. Mu naught by mu naught will give you 1. Whereas if you talk about the relative permeability for iron, it is going to be greater than 1000 in the sense it is so it allows the magnetic field to penetrate through it 1000 times more compared to that of vacuum. Is that point clear? So this is another important parameter for us to understand how good a magnetic substance is, right? Shall I proceed? Okay. So the next concept that we are going to see is magnetic susceptibility. Okay. So susceptibility basically defines about. So the other name for susceptibility is vulnerability in the sense how much a material can get affected in the presence of external magnetic field. So then you can ask me what is the difference between permeability and susceptibility? Permeability is to what extent the material is allowing the magnetic field to pass through it. Susceptibility is the extent to which the material is getting affected because of the magnetic field. So if you are able to, let's say this is the substance, there is a magnetic field in this region. I've taken iron, I've taken copper. Okay. If you place these two in the presence of same amount of external magnetic field, which one do you think will get magnetized faster? I have iron and copper, same amount of external magnetic field, that is a magnetizing field. Which one do you think will get magnetized faster? Iron is going to get magnetized faster. Another way to express it is you can say that the magnetic susceptibility of iron is more compared to that of copper. It's just a language to communicate. Okay. So this is one of the parameters which is used to measure the extent to which the material can get affected by the external magnetic field. Okay. So what does it measure? It measures the ability of a substance to take up magnetization. Take up magnetization in the sense it is going to take up the magnetic field within it. Under what scenario? When it is placed in the external magnetic field. So that is the significance of it. Right. But what is going to be the mathematical definition for it? If you observe, it is defined as a ratio of the intensity of magnetization M to the magnetizing field intensity. It is defined as the ratio of M by H. So basically, if you observe, M is the output, H is the input. Magnetization is the output that is achieved in the presence of H. Is that point clear? So if you observe, right, I can also call it as the efficiency of that magnetic substance. It is something similar to efficiency. I'm just giving us a similarity for you to remember. It is basically output divided by input. So susceptibility speaks about how efficient the material is about to get magnetized. Is the point clear? So it is defined as the ratio of M by M and H, right? So what is the SI unit of this? If you observe magnetization and H, they both have the same SI unit of ampere per meter. So this also has no units or dimensions. So it is also a dimensionless quantity. It is just a number. Okay. Copy it. Clear with this? So this symbol is called as chi CHI, which is a Greek letter. Okay, it is represented with the symbol chi. So I write it as chi with subscript M. Okay. Shall I proceed? Right. Now listen to this. This is the last term that is related to the magnetic substance, which is the relation between magnetic permeability and magnetic susceptibility. That is, we are going to see the relation between mu and chi m. So basically, when you write this symbol, right, you should write it like X only, but right hand side extend it a little bit. Okay. So from the second definition, we know that the magnetic induction is equal to mu naught into H plus M. Accepted? And from the fifth definition of permeability, we know that B is equal to or mu is equal to B divided by H, which implies B is equal to mu into H. Put it here. So mu H is equal to mu naught into H plus M. Is that right? So divide it with mu naught H on both the sides, or you divide it only with H on both the sides. So if you divide it with H on both sides, you will get mu is equal to mu naught into 1 plus M divided by H. Am I right? So mu is equal to mu naught into 1 plus what is M by H? That is what the susceptibility is. So that is what they have asked, relation between magnetic permeability and magnetic susceptibility. So mu is equal to mu naught into 1 plus chi m. Or if you just rearrange the equation and write it, right? So if you rearrange the equation and write it, then mu divided by mu naught is equal to 1 plus chi m. And this mu divided by mu naught is what is called as relative permeability. So relative permeability is equal to 1 plus chi m. Is the point clear? Right. right? So I done copy. Okay. Now we need to understand why we are studying all these things. Just give me a minute. Okay. See, you can ask me a question of why we were studying about all these things, right? So if you observe, we saw the 8 properties, right? So with those 8 points, what we are going to do is we are going to understand how the magnetic substances are classified into different categories. So if you see the main classification that takes place is paramagnetic, diamagnetic, and ferromagnetic substance. Okay. So having said that, I'm going to show you a video. So after this video, what we'll do is we'll prepare a table. So in the table, you're going to answer like how these materials are classified as. Okay, you're going to talk about the properties of them. Okay. Might not think of water as being magnetic. See, observe, okay, observe. Observe what is happening. See, there are different substances that are placed here, right? So you have water, bismuth, cupric sulfate, gadolinium oxide, and aluminum and graphite. Okay. Question is, how are these substances going to respond to the external magnetic field? Okay. So observe how they are responding. So there are two things you need to observe, whether the substance is getting attracted or repelled. Might not think of water as being magnetic, but it is. Did you observe what happened? Might not think of water as being magnetic, but it is. Did you observe? Water was repelled, right? So you have graphite, aluminum, and glass, right? This is a new and different category of magnetism called either para or dia. Different from magnetism measurements. So in general, right, whenever we talk about magnetism, we are actually talking about ferromagnetism. But para and dia are the subcategories. So how you can say is, if you look at paramagnetic substances, they have almost the same behavior as that of ferromagnetic substance, except the fact that the ferromagnetism is more stronger compared to paramagnetism, but diamagnetism is completely opposite. Okay, let's see what is the difference. So you have this, no? So this iron nail is there, right? You connect it across or you put it in the presence of external magnetic field, it will get magnetized. So through this iron nail, what do you think will happen if you try to hold these pins? They will also get attracted, right? Ferro needs iron. If an unmagnetized piece of iron becomes a magnet in the presence of the magnet, right? The effect is strong and lasts even after the magnet is. So did you observe this property? He connected it only for a smaller duration, but what happened is this is still able to retain magnetism in it. So this property of iron or ferromagnetic substance is what is called as retentivity. Remember this term, okay? It's called as retentivity. Paramagnetism is So aluminum, is it getting attracted or it's getting attracted, right?
It's oxygen. Here, I have 2 milliliters of liquid oxygen.
So you saw liquid oxygen also came and got attracted to the magnet, right?
Which sticks to the magnet.
See.
Gallium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnet. An important example of a diamagnetic material, especially made pyrolytic graphite, is diamagnetic field. Don't be confused. This is not static electricity or anything. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a growing crystal of black carbon layers to maximize the diamagnetic effect. Of course, the best diamagnets are superconductors.
So if you look at superconductors, right? Now see what will happen when he drops a magnet into it. So this is actually called as levitation, means it's going to float in the air. So magnet levitation, it's called as magnetic levitation. How many of you have heard of maglev? M-A-G-L-E-V. You have heard of it? Where do they use it? Those trains and all, no? The bullet trains and all, they use this magnetic levitation property. So magnetic levitation means basically it is something like this. It's levitating in the air without falling. It is not falling down due to gravity. At the same time, it is not flying away because of the extra magnetic field. It is balanced somewhere. Sorry? It should be in the... Who told? Okay, let it be that I'm not talking about this example. You're able to see something is happening. I'm talking about this principle being called as magnetic levitation. Okay, this is something used for train, but they don't use superconductors there. There's something else is used. Okay.
Number 83 on the periodic table. The visible power voltage sails toward the weaker magnetic field. Check whether an object is diamagnetic.
So did you understand till this? So now you got some clarity of how paramagnetic, ferromagnetic, and diamagnetic substances respond to external magnetic field. Now, does it make sense of what you have learned? Magnetizing field. That magnet he used, no, that is what is a magnetizing field. And the substances which are responding to them are the magnetic substances. Now we need to study about the different properties about these materials. Right? That is what we are going to put it in a table and try to understand about those 7 points, not even the 8th point, about the 7 points. Okay. Now see, you have a north pole and south pole like this. Let's say you have a magnetic field generated with the help of north pole and south pole. Let's say you're tying a magnetic substance. Let's say you're tying a magnetic substance and holding it. If suppose you hold the substance along the direction of north to south, right? You hold it like this. Now see what will happen to a paramagnetic substance and what will happen to a diamagnetic substance.
Paramagnetic is the lines. Diamagnetic objects like glass will rotate to avoid magnets.
See, this glass is there, no? Had it been a paramagnetic substance, it should start aligning itself in the direction of magnetic field. If it is a diamagnetic substance, it will start aligning itself in the direction perpendicular to the magnetic field because this will never allow the magnetic field to penetrate through it. You would have seen it. What are all the substances that you saw which were repelling it? First, you saw water. Then you had pyrolytic graphite. Then superconductors were there, right? So here, glass is also an example of diamagnetic substance. Observe what it is going to do.
Glass is diamagnetic.
So it is not aligning itself in the direction of field, rather it is aligning the direction perpendicular to the field, because perpendicular to the field will be the equatorial axis. There the field will be lesser. Okay. Whereas you remember what happened to aluminum? Did it get attracted or repelled? Attracted. So but it was not very strong like iron. So it is not a ferromagnetic substance, rather it is a paramagnetic substance. Okay. See what will happen to it. Nobody is even touching it. So did you understand this point? Now the question goes down to, so if you have to answer the question, we need to answer it in terms of chemistry, right? When you talk about a paramagnetic substance, so one of the best examples we saw here is aluminum. And for diamagnetic substance, we can think of water, right? That was the first example that was shown, right? When you think of aluminum, right, what is the atomic number of it? 13. So tell me the electronic configuration. 2, 8, and 3. So there are 3 valence electrons. In those 3 valence electrons, 2 electrons will get paired and there will be 1 unpaired electrons. It is that unpaired electron which is the one which is participating in immediately getting magnetized and exhibiting the paramagnetic properties. Whereas if you take water, so what is the structure? It is going to be like this: no, hydrogen, hydrogen, oxygen. Oxygen has 2 lone pairs of electrons. So it has lone pairs in the sense they are always paired, and then it does not have any unpaired electrons. It is because of the lack of unpaired electrons in water, it is exhibiting the property of diamagnetism. So for you to have paramagnetism, what is needed? You need an unpaired electron. For a material to exhibit diamagnetism, all the materials are going to be, all the electrons are going to be paired. So that is the logic. Okay, ferromagnetic is completely different. It is mostly related to the family of iron. Okay.
So what's it take to understand?
So he's going to explain the same thing.
That's 2s.
So these 2 electrons are paired and 1 electron is going to be unpaired.
It's that unpaired electron that makes it a pair of magnets. This unpaired electron enables it to become a magnet. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet like water? Yes, the water molecule that has all its electrons paired, it will not be magnetized. In fact, water is repelled by the magnet. The electrons come to lower energy and they are put away. In conclusion, something with a paramagnet or a diamagnet is calculated electron. In the case of a paramagnet, it has at least 1 unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
Is the point clear? So I hope you could understand.
I heard the reason I said for your bit like this, what happened with the thing that there is?
Right. Those who are online, could you see it?
Yes, sir.
Yes or no? Those who are
Yes,
online?
Yes, sir.
Sorry, I'm not able to hear.
We saw it, sir.
Okay, perfect. So based on this, we are going to look at how the property of the diamagnetic, paramagnetic, and ferromagnetic substances are going to change in different scenarios, right? Since you saw the major part of it, you yourself can answer this table. And all the questions will be asked in your exam only based on this table. Since you saw it practically, I'm assuming you will remember it better, right? So first question is the effect of magnets. So in the presence of magnets, how does a diamagnetic substance behave? It will repel, and it is going to be a feeble repulsion. It is not repelling very fast. It is going to be a feeble repulsion. Think of water. It is going slowly, right? Whereas a paramagnetic substance will get attracted, but this is also going to be feeble. What about a ferromagnetic substance? It is going to get attracted, but it is going to be very strong. Make sense? Right. Second, in external magnetic field. So when I say effect of magnets means here we are talking about permanent magnets. When we say external magnetic field, it can be anything, right? So in external magnetic field, what will happen? What will happen to a diamagnetic substance? So diamagnetic substance will acquire magnetization, but it will acquire in the direction opposite to the external magnetic field because it is trying to nullify the effect. So if the external magnetic field is like this, then the magnetic field inside the diamagnetic substance will be in the opposite direction because it does not want to take magnetic field. No, it always wants to repel. So if it has to repel, then it should produce a negative effect. That is why if you observe, it will acquire feeble magnetization in the opposite direction of the external magnetizing field. Whereas a paramagnetic substance will acquire magnetization, which is still going to be feeble only. And this time it is going to be in the direction of magnetic field because it is supporting the magnetic field. But what about a ferromagnetic substance? It will also acquire magnetization in the direction of magnetic field, but it is going to be strong. So if you observe, I told you, these two have similar properties, except the fact that this is feeble, this is strong. Okay. And the third point is in non-uniform magnetic field. You saw that, right? When a diamagnetic substance and a paramagnetic substance were suspended, they were placed in the presence of external magnetic field. What happened to them? So in non-uniform magnetic field, what will happen? A diamagnetic substance will tend to move from a stronger magnetic field to a weaker magnetic field. When we placed it along the axial direction, it was trying to align itself in the direction of equatorial. Right? What substance was used there? Glass. Right? So it will tend to move slowly from stronger to weaker parts of the field, whereas a paramagnetic substance will align itself from weaker to stronger. It will try to align itself in the direction of magnetic field, right? Next is, what about a ferromagnetic substance? They will also go from weaker to stronger, but they will be very fast. Paramagnetic will slowly turn, whereas a ferromagnetic substance will quickly turn, right? So fourth point is, what will happen if you place it in a uniform magnetic field? If you place it in a uniform magnetic field, a freely suspended diamagnetic rod aligns itself perpendicular because perpendicular is the direction of weaker magnetic field. What happens to a paramagnetic substance? So if you suspend a paramagnetic substance, it will slowly align itself in the direction of, it will align itself parallel to the field. So here I can use the word parallel, whereas when you use non-uniform, don't use the word parallel because the field lines itself are curved. Whereas when you talk about uniform, the field lines are straight lines, hence you can align, hence you can define an angle between them. But when they ask a question of non-uniform magnetic field, don't mention it as parallel, use the word weaker and stronger. Am I clear with that? So similarly, when you talk about a ferromagnetic substance, it will align itself parallel to the field, but it will be faster, right? Next is, if you talk about the susceptibility, in the sense, the extent to which the material is able to get magnetized, what can you say about the susceptibility of a diamagnetic substance? It is going to be negative because it is never ready to get magnetized. It is trying to repel the magnetic field. So the susceptibility of this material is going to be very small. At the same time, it will be negative. Whereas for a paramagnetic substance, the susceptibility is still going to be small, but it will be a small positive value. Means it is okay, it is saying, yeah, I'm ready to get magnetized, but not at a greater rate. Right? What about a ferromagnetic substance? Susceptibility is going to be very large and positive, and it is going to be greater than 1000. In the sense, it is ready to get magnetized. Now, this word makes sense of what you have learned, right? Next is relative permeability. So when you talk about relative permeability for diamagnetic substance, it is less than 1, slightly less than 1. So relative permeability is going to be greater than or equal to 0, but less than 1. Whereas for a paramagnetic substance, it is greater than 1 and it goes to a small value of 1 plus epsilon. Whereas for a ferromagnetic substance, it is going to be greater than 1000. So what kind of questions will be asked here is, the relative permeability of a substance is 0.5. Listen to my question carefully. Relative permeability of a substance is 0.5. What material is it? It's diamagnetic because it is between 0 to 1. So susceptibility of a material is minus 0.5. Negative dia. So this is how they'll ask the questions. Okay, for that you need to know this table. Right? So I think we are done with relative permeability, right? Yes. So when you talk about the permeability value, so permeability of a diamagnetic substance is always less than mu naught, right? Because what is relative permeability? Mu by mu naught. If mu by mu naught is less than 1, then mu is less than mu naught. Correct? This is mu divided by mu naught. When this is less than 1, mu is less than mu naught. Whereas for a paramagnetic substance, mu is greater than mu naught. And for a ferromagnetic substance, mu is very much greater than mu naught. It is very much greater than mu naught. And the eighth point is the effect of temperature, right? So when I talk about the effect of temperature, we talk about the susceptibility of that material. We don't talk about the permeability. It is about the susceptibility because we need to know the extent to which the material is going to get magnetized, right? So when you talk about a diamagnetic substance, susceptibility is independent of temperature. Whereas for a paramagnetic substance, susceptibility is inversely proportional to temperature in the sense the temperature increases, the magnetic property of the material will decrease. Whereas for a ferromagnetic substance, it is also going to decrease with temperature, but in a slightly complex manner. How is it going to be? The susceptibility is going to be inversely proportional to 1 by T minus Tc, where this Tc is called as Curie's temperature. Curie apostrophe S, Curie's temperature. Is the point clear? So the ninth point is, what will happen if you remove the external magnetic field? See, suppose there is glass or water. When you take, suppose there is water, okay. When you took the magnet closer to it, the water was repelling. As soon as you remove the magnet, what will happen to it? It will stop there itself. It will stop there. It will not come back. It will stop. In the sense, when you remove the magnetizing field, we can say we can say that the magnetization is lost by the material. So magnetization is going to last as long as the magnetizing field is applied. As soon as you remove it, it is instantly going to lose its magnetization. Same is going to be the case for paramagnetic substance, whereas for ferromagnetic substance, magnetization is retained even after the magnetizing field is removed. You remember that nail, with the help of that nail, he caught some bell pins, right? Then when it was taken up, what happened? Even after the removal of external magnetic field, the pins were still attached to it, right? It is because of this property. What did I say this property is called as? It's called as retentivity. It's called retentivity. Am I clear with that? Right. The next point is variation of M with H. So if you observe, what is the definition for susceptibility? It is M divided by H. So what will be the relation between M and H? M is equal to susceptibility into H. So if I take M on y-axis, H on x-axis, and if I call the susceptibility as M, is it not looking like the format of y is equal to mx? So y is equal to mx means what do you expect? You expect a straight line, right? So what is going to happen here is, for a diamagnetic substance, M changes linearly with H. For a paramagnetic substance also, M will change linearly with H, but after a certain amount of time, it will attain saturation. In the sense, if I draw the graph for this, then the graph will look like this. It will be straight. After a certain point, it will attain saturation. When you draw the variation between M and H. So M is the output and H is the input. Is that point clear? So M changes linearly with H and attains saturation at low temperature and in presence of very strong fields. And what about a ferromagnetic substance? For a ferromagnetic substance, M is not going to be linear at all. Rather, M will be this, the one you need to make a note of. See, observe, when you plot the graph between M and H, right, for ferromagnetic substance, the graph will be like this. It will not be linear. It will be like this. The reason for it is, since this has a very high permeability and susceptibility, what was the susceptibility of it? It was greater than 1000. So since it has a very high susceptibility, even lesser amount of magnetizing field is enough to magnetize this material. That is why the graph is not linear. It will go above the linear curve. So when I say not linear, right, Suppose in the option, they give this, no, this is wrong. Suppose this comes in MCQ, they give you this graph and ask you to choose which is right. You should not choose this one. Because what is happening here? This is telling you that more amount of magnetizing field is needed to magnetize the material. Whereas this one tells you less magnetizing field is enough to magnetize the material. Means lesser the value of X, more is the value of Y. Whereas here, more is the value of X, lesser is the value of Y. So this is wrong. Am I clear with this point? Right? And there is something called as hysteresis effect, okay, which I'll explain later. The next point is about the physical state of the material. When you talk about a diamagnetic substance, we saw diamagnetic substance was water, right? So it can be either in the form of solid, liquid, or gas. Same is going to be the case with paramagnetic, whereas for a ferromagnetic substance, it is going to be solid only. So it is normally going to be a solid. Okay. And the examples of diamagnetic substances are bismuth, copper, lead, silicon, etc. All these points that are given here. Similarly, for paramagnetic, aluminum, sodium, calcium, all these things. And for ferromagnetic substance, iron, nickel, cobalt, or you have alnico. What is alnico? Aluminum, nickel, and cobalt. It is a combination of all these materials, right? So these are all the examples of ferromagnetic substances, right? So this is all about the important properties that are associated with dia, para, and ferromagnetic substances. I hope I'm clear with this, right? So did you understand why we were learning about those terms? Right. With this, actually, we have completed the chapter. It's full of theory only, I told you, no? The chapter is over. But hysteresis alone, what I will do is I'll explain it later because that is deleted. There is something called as hysteresis loop, which is important for you to understand soft iron core and hard iron core. If you remember in galvanometer, what was the core that we used? Soft iron core, no? The reason why we are using a soft iron core is because it has less hysteresis. It has less hysteresis. That is the meaning. About that, I'll slightly explain. Maybe I need 15-20 minutes of time to explain it. Okay. But since this is important, first I would suggest you to absorb this concept. Is that clear? So you can just make a quick note of it. Put your book in the landscape mode. Just tilt it. Okay. Put a table and start writing it, but make it fast. Elasticity. Ama. Adeda. Lagging. Yeah. No, Ashra, what happened? I can send, but you write. Evidra, there is a reason I asked you to write. At least write down the keywords. Don't write everything. Don't copy everything. How will you write effect of magnets? Feeble repulsion, feeble attraction. Don't copy it. 11 by the way, 13 points. Done with this slide? Yeah, send this. But you'll write it, that's my doubt. Okay. Well, we can get started. Okay. So if we start with the next one, that is electromagnetic. And that chapter has a lot of derivations, mathematical values, more of these beyond that. Okay. Then we wind up. Those are online. Is there any question?
No, sir.
Okay. Wind up.
Thank you, sir.
Yeah.
Thank you, sir.
1 minute. Wait, 1 minute only. So, sir, online, are you able to hear me? See, in your 10th grade, you remember this chapter that you have learned, that human eye and colorful world. You learned about the eye, right? Deleted, but a basics are தெரியுமா? Like the pupil பத்திலாம் தெரியும்ல? What will happen? தெரியுமா இல்லையா? Light அடிச்சா வந்து become small, right? So why I asked you to wait is, so last week we conducted a workshop in one of the schools. This for a 10th grade. ஏன் கண்டில்லாம அது? Okay. Okay. One of the 10th standard students, I asked them to come club together and do this activity and send it to me. See what they have done. சிரிக்காதீங்க. See, did you observe? Did you observe the pupil? So when the brightness is more, it is becoming small. You're able to see that clearly? A tangent galvanometer. உன் பேர் அதுதான் இன்னிலிருந்து. உன் பேர் அதுதான் இன்னிலிருந்து. See, why I'm showing this is, one, to motivate you, obviously. Second is, second, today I showed you something, right? A YouTube video, right? Using a magnet and the different substances. I want somebody to take responsibility and do that as a small project for me and give it. I'm not saying one person, right? It can be as a group also. சரியா? வேலை வெட்டி அப்ப வேலை வெட்டி அப்ப இந்த பொண்ணுக்கு வேலை வெட்டி இல்லையா? அடிச்சு பல்ல பேசுறேன் வேண்டா? She has worked hard. 10th standard student உட்காந்து ஒர்க் பண்ணிட்டு just with one guidance she has sent it to me. இருக்கட்டும். அது அந்த டைம்ல உனக்கு அதிகமா தான் இருந்தது. கிழிச்சிட்டீங்களா அந்த டைம்ல? 5 லட்சம் தானே கிழிச்சிங்களா? இல்ல இல்ல, கஷ்டம் தானே அந்த டைம்ல. அதே மாதிரி தான் இப்போ இன்ஜினியரிங் போனால் 20 லட்சம் அதிகமா இருக்கும். அந்த ஏஜுக்கு தகுந்த மாதிரி இருக்கும். அது எதுவும் பண்றதுக்கு இல்லை. புரியுதா? ஸோ ஐம் சேயிங், like if you can work on it, need not copy the exact materials that are used there. I've given you some examples on all those things, right? We have all the materials here. If you can actually do that as an activity and give it, we'll see how much you people are actually able to work. Work பண்றீங்களா ஏதாவது? ரெடியாவே இல்லை. ரிப்பல்சன் உட்காந்து டான்ஜென்ட் கேல்வனோமீட்டர் பண்றாங்க ஒருத்தன் பண்ணிட்டு பேர். டேய், டான்ஜென்ட் கேல்வனோமீட்டர் பண்ணுவேன். சொல்லு, என்னது இது? நான் பண்ண சொல்லடா, உனக்கு கான்செப்டே புரியல. இப்ப நான் வந்து ஒரு வீடியோ காட்டினேன் மேக்னெட்டிசம்க்கு, அந்த வீடியோ அதை பண்ணி கொடுங்கன்றேன். எதுக்கு எதுக்குடா இது? அப்ப யாரா நீங்க? எங்கேந்திரா வரீங்க?